Okay, welcome back. Next, in our large-scale groundwater day, we have Christian Moeck, who's from Moeck, which is the Swiss Federal Institute for Aquatic Science and Technology. And something like that.
Yeah, something like that, yeah.
And he'll be giving our next talks. Welcome.
Yeah. Thanks a lot. And maybe I start with information. 2 days ago, Maria and Camille, they told me, please remember your talk will be a little bit shorter, and I think it's great because it will be the first time that we all will be on time at lunch. So I think this is good. And it's probably the first highlight of my talk. And yeah, actually, I will talk today about groundwater recharge rates, groundwater recharge estimation. I will talk about different scales. I will just show you a bit the limitation we have on the field because we use relatively simple methods to estimate recharge. We just have indirect methods, and there's a huge uncertainty. And then we move on to the global level, and we will try to understand if we already have this uncertainty on a field scale, what is the uncertainty and the limitation and restrictions we have on a global level, especially with models, because we use normally these models to make prediction. How good are our predictions about climate change? Before I start, I would like to just give you a few slides, kind of a general introduction. What is groundwater recharge? Why is groundwater recharge important? And also how we measure groundwater recharge. So I think you have seen this graphic already many times here. And the question is, how is groundwater recharge defined? When you look in the literature and textbooks, you can read groundwater recharge is the infiltrated water that percolates through the unsaturated zone and reaching the water table. So actually, it's water from precipitation which infiltrates here through the soil, the vadose zone, and then is reaching the water table. And when you see this graphic, it's also clear if the component of the water balance change, like precipitation, evapotranspiration, surface runoff, and so on, groundwater recharge will also change. We have basically two mechanisms or types of groundwater recharge. One is called the diffuse recharge. This is what I explained before, the direct vertical infiltration into the subsurface, reaching the water table. And on a larger scale, we can say, well, this is fairly evenly distributed. I know this is not 100% correct because we know we have macropores, we have preferential flow paths. That's why we also have models like dual porosity, dual permeability. But it might be correct when we compare that to focused recharge, because focused recharge is the recharge coming from surface water, water from rivers or creeks, infiltrates into the subsurface and recharging our aquifer. And for the surface water, we can make or define three different conditions. One is the connected condition, one is the transition, and one is the disconnected. I think this is also quite important to understand. This is highly nonlinear. When we are pretty close to the river with the groundwater, so the head difference are small, we have a certain infiltration. When we go away from the river, the infiltration will increase until we reach kind of a transition zone. And then at the end, we are far away, completely disconnected. And here, our infiltration rate is more or less constant. But I will not talk today about this process. I will really mainly focusing on this more diffuse groundwater recharge. So perhaps some words, because when you look in the literature, you can find different terminologies, different words for recharge. And I think for me personally, I think it's important to make the difference. When we talk about infiltration, this is really just the water which infiltrates into the subsurface. This more potential recharge can become recharge at one point, but it can be also be back transferred to the atmosphere by root water uptake, for instance. The plane, horizontal plane, which makes the difference between upward and downward flow, it's called the zero flux plane. It's not constant over time, that's also clear. And it's because we do not have so many measurements in the field, it's difficult to estimate, and sometimes you mimic or use you mimic somehow this zero flux plane by just assuming it's the bottom of the root zone. And all the water below the zero flux plane, it's called drainage, percolation, or net infiltration. And at one point, it's reaching then the groundwater table, recharging our water, so providing some input. And this is then groundwater recharge. And yeah, why is groundwater recharge important? Why I think it's something we have to investigate. Just a simple example, here we have the continental US, and this is our groundwater recharge. Finally, our input to the aquifer. In red you see relatively low groundwater recharge rates, in blue relatively high. And when you then just compare, I know the units are not exactly the same, but just the color is important here. When you just compare that to the abstraction rate, so the water we take out, you nicely see, for instance, here the high plane aquifer, which is used for agriculture production a lot. And when you just compare this, we have relatively low recharge rates and relatively high abstraction rates. It's also not a surprise that in this area we have declining water table. Then why is recharge also important? Because still in many models we need groundwater recharge as an upper boundary condition. I think this is quite important. Of course, we have more integrated models, physically based, fully coupled models like Parflow or hydrogeosphere, for instance, and they are partly, well, on the long term they will solve the problem, I'm pretty sure. But because these are integrated models, it's quite difficult just to extract the groundwater recharge rates. I had really, during my PhD a long time ago, I really had problems to just find a way to estimate groundwater recharge in, for instance, hydrogeosphere. And with some post-processing, of course, you can get a flux. And what I've done, for instance, was to create a plane on the water table and just calculated the flux through this plane, and then I had my groundwater recharge. And unfortunately, recently a paper came out which shows, well, this is not correct. And I'm just happy that I have already my PhD, because my results might change a bit. And they really show, well, the issue is with the capillary fringe, so we just can estimate in the integrated models some kind of potential recharge. But still, these models are extremely useful, and I think it's also the way we have to go. Then groundwater recharge, of course, when we have water which infiltrates into the subsurface, it's also clear that this water might contain contaminants, right? When we have a lot of infiltration at agriculture areas, of course, water might have some contaminants included and is contaminating our aquifer. And for instance, here, this nice study from Joel Podolsky, he's at our institute. He used tritium data measured here in this area in the Sahel zone, and they calculated a probability of tritium in the groundwater with some machine learning approaches. And tritium has a half-life time from 12.4 years, so we can measure tritium in the last 50-60 years. And when we find tritium in the subsurface, of course, we know some recharge occur, and when we have agricultural production here, there's some kind of aquifer vulnerability. But actually, I don't like this word vulnerability, because at the same time, of course, you might contaminate your aquifer, but if you do not have water and not using that sustainably, it's also some kind of vulnerability to the system. How we estimate groundwater recharge, there are many different methods, and I choose just some more, say, common use methods. Again, very simple. We have on one hand the water table fluctuation method. You have your groundwater level here, you have a declining groundwater level, then you have a precipitation event, the level rise, and you can calculate or estimate the recession curve, and then you have your delta H. you multiply this term with the specific yield, which is just the drainage from a volume, and then you get out your groundwater recharge. But it's also clear just from this simple equation, small errors here has also directly a consequence for groundwater recharge. So if we just double the specific yield, we have double the double amount of recharge. This is certainly a problem with these kind of methods. A method which is more used in arid, semi-arid areas, again, this is I think the high plane aquifer. It's the chloride mass balance approach. So for this method we need the rate, the amount of precipitation. We need the concentration in precipitation, including the dry fallout. We need, for instance, soil samples from the pore water chloride concentration, and when we have this, we can calculate a drainage. And if you have a lot of points, then you can make some nice interpolation, and then you get these kind of maps.
Can I ask a quick question on that?
Yeah.
The R, is that a rate or a depth? I'm surprised by the delta T.
This one.
Yeah. It's a rate, I guess, that's a rate of recharge, or is that a depth of recharge?
It's
just over interval.
yeah.
So it is rate.
It's a rate.
Okay.
That's a rate.
And then, of course, we can also model groundwater recharge. There are a variety of different approaches, and especially on a global scale, often some kind of bucket models are used. So, in fact, you have just a bucket, you have perhaps some macropore flow, macropore recharge, you have recharge with a defined delay, and some of these models also mimic a bit the Richards equation. Instead of having here the water content, you have the volume of the bucket, and that's why you can still simulate somehow some nonlinear processes, but of course these parameters often have no physical meaning or less physical meaning. And then the models which are normally used for small scale or field scale, the Richards based equation models. I think you have already seen these equations many times. I just remember Kino has a quite similar slide, and it's just important that you know these kind of models are also used. So, in fact, we have different methods to estimate groundwater recharge. Some are based on the saturated zone, including some tracers, some physical approach. Some are based more on the unsaturated zone, and some also use surface water to extract groundwater recharge rates. And it's also important to understand that not every method can be applied everywhere. Some methods are, they show more the area. They can be just applied for small scale. Some methods are better used for large areas, the same for the years. Some will give kind of a long-term groundwater recharge rate. Some can be also used for small fluctuation groundwater recharge, and also fluxes is important. With every method you can't estimate exactly the same for the same flux. You really have to be careful here. But I think important again is that all the methods apart from the lysimeter, these are indirect measurements. So we have no observation effect about groundwater recharge, direct observation, which we normally have, for instance, for discharge values in rivers. So yeah, recharge is important, but it also varies in space and time, and it's really difficult to measure directly. I think this is quite important here. And just to understand a bit the uncertainty in recharge estimation, we carried out a small scale, for me small scale, I mean for you perhaps not, a small scale study in northern Switzerland at the Prealps, and here we are using these nice lysimeters. And lysimeters are a soil column, so you stick in the soil cylinder the steel cylinder, not soil, sorry, the steel cylinder into the soil, you try to have undistributed soils, which is not always the case, but you're trying that, and then you're mimicking the surroundings or different vegetation on top of the lysimeter. And then at the bottom, there are different concepts. You can apply a certain pressure, or you also have a kind of a free drainage where you then finally just measure with a tipping bucket groundwater recharge rates. And we use this groundwater recharge rates from the lysimeter as a kind of reference case. Of course, lysimeters, there are also issues. You might have flow at the walls. The bottom boundary is not completely as the same in the field, but we decided to use that as a reference case because this is the only chance we have really long-term measurements, time series of groundwater recharge. And here you can see our groundwater recharge rates for more than 20 years, annual millimeters from the lysimeter. And then we applied different methods. For instance, the RORA method, which is based on surface water extraction, so base flow separation. We used the water table fluctuation method I explained before. We had a relatively simple soil water balance model. Then we have kind of a semi-mechanistic model, which is often used in global models. And then we have the physically based model, hydros, but 1D and also homogeneous. And what we also have done then is to calibrate the model. So all the different methods and models with a star are calibrated against our recharge from the lysimeter. And the one without the star is just based on literature values and to a certain extent best guess for the parameters. And what we observed, of course, we have huge ranges. I mean, you see here's the mean of groundwater recharge from the lysimeter. It's around 1,000 millimeter per year, which is already quite a lot. But we have also quite a lot precipitation in this area. And the mean is not so bad for some methods, but then if you see just the box here, the box plot, it varies a lot, especially for the surface water models, the water table fluctuation method, uncalibrated with a specific yield, just the best guess. Literature value is completely out. When you calibrate, you come closer, but it's not really a perfect fit. You might say, well, the physically based models performs best, but also these models are still simplified because we just have homogeneous parameter distribution. When you then look on the time series, so we have here now, I think 12 years plotted for the calibrated case. At least you see all the methods shows the right interannual variability. This is good, but the absolute values are different. And because we have this difference, normally we are not only interested for water resource management in absolute values, we want to make also some decision with these values, with the data. And what often is done is we would like to understand how sensitive is the system, for instance, to drought. And for instance, here you see the concept. You have, for instance, here one variable, our groundwater recharge rate as a time series, and then you define a threshold, and you say all the values below this threshold can be considered as drought. You can also do that with surface water or groundwater levels, and then you see the duration of the drought. You can estimate kind of a deficit volume, and also what is the intensity of the drought. And just when we apply this for our different methods, we see again a highly variable result, and it's really difficult to say how should we manage this site in terms of drought conditions. So just again, this is just to understand a little bit how uncertain are already our observations, our measurements in the field. And it's not only us who estimated this huge variability. It's also other studies, and here again I think it's quite impressive when you use just from some maps groundwater recharge for a location. You have 100 millimeters. When you apply different methods, you have up to 800 millimeters per year. So on our field, already with our simple methods, because we have normally no observation, we have a huge uncertainty. And the question now is, how does it look now on the global scale? Because on the global scale, we even have more difficulties and simplifications and less data. And yeah, well, I also started to collect my free time some data points because it's really difficult to get funding for that. Everyone is interested, but no one wants to pay. And yeah, I started to collect from the literature groundwater recharge data. And in total, we have more than 5,000 data collected. It sounds good, it's a huge number, but still 5,000 on a global scale, it's still limited. We were trying to avoid groundwater recharge estimates from the literature which are less than a year, so we were really focusing, we want to have millimeters per year at least, best would be longer time series, and, but they are normally not available. We were trying to avoid areas or estimates where we know they are impacted by irrigation or managed aquifer recharge, because we wanted to focus here really on the natural occurring groundwater recharge. And also we were trying to omit areas which are dominated by rivers and streams discharge into the groundwater. So again, the focus is more on the diffuse groundwater recharge rates. And most of the data we collected, you see also the bias. We have a lot of data here in Australia, some in South Africa. The US has also a lot of data. South America, it starts to be difficult, and this area is completely blind. And the methods which were used from literature are mainly chemical tracers, so the chloride method or the water table fluctuation method. And just remember the uncertainty we already have here on the field scale. Good, then because we have now this data, we also extracted available global variables like annual precipitation, evapotranspiration, aridity index, seasonality in precipitation, and so on and so on. And we started just to plot it in a very simple way, XY coordinate, XY plot. And for instance, with the precipitation, yeah, there seems to be a trend, but it's certainly not linear. It's more complex than some models normally assumed. And especially here with the aridity, we found this trend super interesting, and then we started to further investigate this. We applied or we splitted the data in percentage of recharge rate over a certain threshold. We used some, to a certain extent, arbitrary thresholds, but it still mimics a bit the climate. Recharge rates over 100 millimeters, 500 and 300. And we found, of course, a negative trend between aridity index and recharge rates, because when we are here at this point, then we are in very arid areas, and when we are more to 1 or 2 to 1, we are more in humid areas. Maybe I forgot to mention how the aridity index is written. It's potential evapotranspiration divided by precipitation. And we also saw, well, there is always a correlation, but the correlation is less strong, for instance, for the groundwater recharge rates over 500 millimeters, where we just observed that it's likely we have so much water that surface runoff also occur, and the process is less pronounced compared to the different other thresholds. And we have done this for all the different influencing factors, and one was really, it's also not surprising because this is the input and output, precipitation and ET. Aridity index was quite strong. We found a very strong correlation. And then we thought, well, if this is already such a strong correlation, why not using this and trying to reproduce on a global scale our groundwater recharge rates? So what we have done, we used a simple equation, a sigmoid equation. We first started to use recharge fraction, so recharge divided by precipitation. We plotted the recharge fraction against aridity, and you see also the gray points, a lot of spreading, yes, but then we started to bin the measurements. So we have the equal amount of measurements for all of the bins in a different way. And then we started to fit our simple sigmoid equation. And the sigmoid equation shows just, we have our recharge precipitation ratio, so recharge fraction. We have a factor alpha, which shows just how much of the precipitation will be recharged, and it's also constant, so super simple. And we have our aridity in the equation, and our beta, which is just the exponent of the sigmoid equation. And what you see, again, the fit is not so bad. Just after here, we realized the regime might change, and we will just provide information where we still have a good fit, because everything here was just too uncertain. And based on this simple equation, of course, we could calculate groundwater recharge or recharge fraction or absolute groundwater recharge rates. I think this is not so interesting. It's just a map. Of course, Australia has relatively low groundwater recharge rates. Apart from the coast, the tropical areas, we have higher groundwater recharge rates. But more interestingly is how this simple equation performs compared to global models. And this is actually the result. We collected or extracted from global models the groundwater recharge rates, and here's the plot between modeled recharge in millimeters per year against observed recharge. The 1-to-1 line shows a perfect fit, and here in black, of course, we calibrate our model against our observation, so we are pretty close. But more interestingly is that the other models show an underestimation, a complete underestimation of groundwater recharge. And then we started to think about why this is the case. And we found out that these models are not calibrated against recharge. If they are calibrated, it's normally against ET measurements from satellites or discharge values from big rivers. And some include some kind of recharge, but it's more a proxy. They use stream flow measurements with some base flow separation, or for instance, one study had 16 observations to calibrate for a global model against groundwater recharge. And we found also interesting when you see just the mean groundwater recharge from our observation, it's around 200 millimeters per year. And then if you see the other models, also a machine learning approach, it's completely off. So our observation-based recharge values more than double the global model estimates. And this is quite important because you mentioned that we have this feedback mechanism with the atmosphere, and this also means that we have more recharge which interact, because the water balance of course must be close, we have more recharge which interact with evapotranspiration and also discharge, stream flow. Right. And just one study I found just when I was here, sitting on the beach, just published recently, and they also show it's not only a problem for groundwater recharge, but here we also have an estimation of overestimation of river discharge. And I still have to read the paper carefully, but if you just take the numbers quickly and see the overestimation and our underestimation, it seems to fit somehow. So it might be that when we improve this, we might also improve our groundwater recharge estimation on the global scale. Okay. So, well, this was the historical data. This was kind of a snapshot, a historical snapshot. But normally we have models also to make predictions. And we thought, well, if the models already perform not so well for the current or historical condition, how do they perform then for the future? And for this, we wanted to calculate the sensitivity. We again used our simple sigmoid equation here. Of course, we do not have time series of groundwater recharge, therefore we trade time for space and estimate the sensitivity of recharge to aridity between different places, which is shown here. And when you see this equation here, it's also clear that we somehow lumped recharge precipitation to precipitation in T. We cannot really make the difference. What is now the driving forces for changes? Is it precipitation or is it ET? And therefore, we calculated elasticity for precipitation in ET. The equations are not so important. Important is just with this, we can now also estimate or assess how important are changes in precipitation for future groundwater recharge and how important are changes in evapotranspiration for future groundwater recharge. So, right, again, maybe let's start here. Here we have our aridity index again against our groundwater recharge fraction. In blue are our observation, as you can see here. And then all the other lines are showing the different models and also our sigmoid simple equation. And what you see, well, aridity index higher than 2, well, there are differences, but still pretty close, and it's also more or less a straight line. But then after aridity index 2 up to 1, we really see a huge difference between the different approaches and the different models. And when we now calculate the sensitivity, it's the same plot, but here we have now the sensitivity. We see exactly the same trend up to a aridity index of 2. It's still okay, and then we have really a spreading, sometimes in an opposite direction. Good. And then we were running some multi-model projections for the time slot 2050, 2018, and also for a historical period 1980 to 2010, and for a low emission scenario. And with this we can estimate the difference between these two time slots, right? For this 30 years and these 30 years. And when we now have this difference in precipitation and ET to the reference, we can simply just multiply that with the elasticity, and then we get out these maps. The precipitation induced recharge change for this multi-model projection, and the evapotranspiration induced recharge change in percentage. And the color scale is exactly the same between them. Of course, evapotranspiration, because we take water out, is in a negative direction, and this is mostly in a positive direction. And just from the colors, you already see that changes in precipitation are more important than changes in evapotranspiration. When we then make the combination here, we see what are the total recharge changes expected. And we think this kind of calculation can be helpful for using as a benchmark also for global models, just to see, make a model comparison if the model perform quite similar. And I think it's also interesting just from the ratio in general, 1% increase in precipitation leads to 2.2% increase in recharge. And this also shows which areas might have more recharge on the long term and which has less and are therefore vulnerable. But what we have done now is still somehow kind of a static assessment of the impact of climate change, the impact of climate variability. And of course we know that climate can also change on long term. So we have some climate variability, and I think this is also clear for everyone. We have these large scale climate teleconnections, right? For instance, the El Nino Southern Oscillation. And with the El Nino Southern Oscillation, for instance, we have then in some areas more wet condition and in some areas more dry condition. And this is also what we can observe on the surface. We might have droughts or we might have flooding. And this is clear. But it's interesting that, and this also has an impact, of course, on our groundwater recharge rates. But it's also interesting that for some piezometers, some groundwater level, they do not fluctuate. We have on the surface this variation, but they do not show really a response. And the question is a bit why, and we believe it's due to a damping in the unsaturated zone. And we developed a simple conceptual idea. So we have on the surface some variation in groundwater recharge. We have kind of a long-term mean groundwater recharge rate. This is our QS. And then we have some periods, the QP, the fluxus changes. And then with increasing depth, at one point, we are pretty close. It's less variability, and we say, well, this is kind of a damping depth here. We have only 5% of variation of the surface variation in this depth. And if our groundwater level is now below this damping depth, then we have steady state condition. And if the groundwater level is above, of course, we have transient condition. And I think this is important also for setting up global models, global circulation models. How much can you simplify these models? Because sometimes you might speed up the models by just putting some areas on steady state. But it's also important for groundwater management, because we have to know where can we calculate with a long-term mean, and where we have also to be considered the variability. Because it doesn't help if you say, well, in average, well, we have enough water, but then certain periods not. And we use that, or we applied it by using an analytical solution to the Richards equation for the Vados zone. The hydraulic conductivity and soil moisture is based on the Gardner-Cosney model. And we needed an input. And again, this is our input. This is the time. This is the input. We have a long-term QS. We have a period. And with a certain magnitude, this QP. And when we have this input, we will end up with this infiltration front. And again, at one point, we have a damping. And this analytical solution was developed by Mark Barker and Niebuhr, and also used by Jess Dickinson and Ty Ferry. And if you want to understand a bit more about the analytical solution of the Richards equation and this whole calculation, it's really an excellent paper of Mark Barker. And just to give you some ideas how the setup is, of course, we have the one-dimensional Richards equation, so just in the Z direction, so with depth. We have our vertical infiltration, which is defined as this. So we have our long-term groundwater recharge, we have our QP, and we describe the period with a sinus curve. Then we have our hydraulic conductivity function with the Gardner model, and our water content is a function of the pressure head with the Gardner-Cosney model. So still relatively simple, and of course it's 1D, it's also homogeneous. We neglect all these macropores and preferential flow, but we simply apply that. Maybe just in addition, as you already have seen, the damping increase, of course, with depth, and for this we need the depth and our lambda, and the lambda term is based on, or is highly variable, or depending on alpha, on the Gardner soil parameter, and on one non-dimensional term, which is shown here, which also include the diffusivity. And for using this analytical solution for the Richards equation, we had to linearize the diffusivity term. But again, it's very well explained in a paper of Mark Barker. So what is the sensitivity of the damping factor? We have different soil textures, clay, we have sand for different periods, 30 days, 90 days, 1 year. We have the depth on this side, and we have the different groundwater recharge rates on this side. And a damping factor of 1 means we have no damping. The signal is the same like we have on the surface, and damping of 0 means we have no signal. And just here for sand, for instance, you can see if we have low groundwater recharge, we are reaching quickly with depth almost complete damping. When we have high groundwater recharge, the damping is less pronounced. When we then look, instead of period 30 days, we go to 90 days, you see this curve change a bit, and the damping is different. So it's a function of the depth, it's a function of our long-term groundwater recharge, of the different soil texture, soil parameters, and of course also of the periods. And this method, this analytical method, was tested against some physically based models like hydros, ComSoil, based on the Richards equation, and quite successful. Of course, there's some difference because we have some simplification in terms of linearization in the equation, but it's working. And we thought, well, if this works as a 1D location, why not applying that also on the large scale? Because all the information we need for the global scale are available. And yeah, I think you know this work here now. And so we took from literature the information for depth to the water table, the long-term groundwater recharge rate, soil texture from Hegel et al. And we had the soil texture, and then we had lookup table just to have then the different parameters we need for our analytical solution, and also different periods of flux variation. And the periods of flux variation are monthly, seasonal, annual, and then we have the longer flux variation, the periods 2 years, and also, for instance, here 7 years, which is quite similar to El Nino effects. Of course, we are not searching an El Nino signal in Northern Europe. That's clear. It's just to understand a bit where this number is coming from. And then we have also decadal periods. And all these periods are found on different locations in the world. So we have these periods in our groundwater levels. And because groundwater recharge is so uncertain, we used not one input, we applied all the available inputs we have. So in terms of workflow, we have our long-term groundwater recharge, which goes into an analytical solution. We have the soil texture with the different hydraulic parameters. We have the different periods. We calculate then the damping depth, and then simply we compare the damping depth to our groundwater table depth. And we are not doing that on one location. We do that for every grid cell on the global scale. And what we then get out, for the damping depth, we have relatively shallow damping depth, which is not surprisingly all over the world, just a few meters. But if we then look on seasonal scale or half annual, annual scale, you already see some differences. So damping, the damping depth is deeper in more tropical areas. It's less in these areas because we have also less groundwater recharge, and with this you have the different estimates. And now we can simply just compare this map with this map and can figure out or flag where we have steady state or transient condition. And this is shown here, but I think this is not so interesting. This perhaps also not, because the different models we have difference because of the different recharge rates, but at least they show the same tendency, the same trend, and I think this is most important here. But I think more important is finally this map, because this map indicates the shortest time scale at which the groundwater recharge rate at the groundwater table remains transient. And it's some kind of a response time, a transient time of different areas to changes in groundwater recharge and changes of the period. And for instance, here in Europe, you see groundwater recharge rates conditioned varies on monthly, seasonal, up to half annual scale. in some other areas, for instance here, we will assume or we predict that the groundwater table just varies on annual or to multi-annual scale. And with this, we get some kind of response time of the different areas just based on this relatively simple calculation. And then we can extract all the values. So here we have groundwater recharge in millimeters per month. We have the damping depth, the different periods in different colors. Of course, we have some spreading because we have different soil texture. And if you know now that you have 1 millimeter recharge per month and you want to observe monthly variation, you will end up with a damping depth of just a few centimeters up to a meter, depending what soil type you have. And when you now your groundwater table is in 10-meter depth, there's probably no chance to observe any fluctuation in the groundwater table. Of course, our model is simplified, it's homogeneous, it will never be completely correct, but if you have, for instance, preferential recharge and you know you increase your recharge to 10 millimeters, you still can make some kind of guidelines or estimates for you. The big problem with these global models is always how to validate your calculation. I mean, the problem here is a bit, it's a nice tool. I can play a bit with this tool, with the analytical solution and get some results. But I'm fully aware that it's very, very simplified and do not account for soil heterogeneity or preferential flow or layered heterogeneity. And to at least check if our results are plausible, we further collect from literature studies, I think in total around 100, which investigated these periods in the groundwater levels with some wavelet analysis, and this is shown here. So we have the percentage, how many times we were right with our analytical solution and how many times we were wrong for annual, 2 annual, longer scale, and 7,300 days. And what you can see here, well, 20% we were wrong from 16 only observation, but 80% we were right. So it's not bad. And when we increase now the period, we end up to a value of around 90%. And we believe we have this increase because on the longer time periods, longer time scales, soil heterogeneity becomes a bit less crucial. It's still important, but we have this huge fluctuation, and therefore, even though our method is very, very simplified, we came up with a at least plausible result. Good. We are already almost at the end. So I hope you have seen that we need reliable estimates of groundwater recharge, but groundwater recharge very significant across different locations and also over time. So that's really the problem a bit, and we do not have direct measurements. So every calculation, every planning we do will lead to inconsistencies of the results. We have a lot of input uncertainties, and the model complexity also, I think this is more important, also gives us sometimes completely different trends, especially when we make prediction with climate change. I think this is quite important. We are not searching, especially on the global scale, for the absolute, the right value, but the pattern and the trends is important. And certainly here we have to still improve our work. On the global scale, groundwater recharge is underestimated, but very significant. And this, of course, has feedback mechanisms for the atmosphere, for groundwater surface water interaction. On a small scale, we might have control on that mostly, but on a global scale, not. And then again, the global uncertainty and also lack of data. Yeah, this is really a challenge for making robust estimates and especially predictions. And I didn't do the work alone. I hope I not forgot someone. These are my colleagues from different universities, and yeah, with this, it's almost over. Thank you.
Right, thank you, Christian. We have time for questions.
I really like the idea of the sigmoid model. Can you explain the physical intuition behind it? How you got there?
You like the idea of?
The sigmoid function that you use
Yeah.
to model, was it aridity index versus groundwater recharge?
Mm-hmm.
Can you explain the physical intuition? Is there any, or was it just a fitting exercise?
It's actually just a fitting. There's no, not, well, I mean, of course it reproduced, sorry, give me a second. It reproduced this pattern, but at the end it's more a fitting. It has, again, almost no physical meaning. I mean, also this parameter alpha, which makes the fraction of precipitation becoming recharge constant. It's a totally oversimplification. But for me, important was just to show, even with this super simple fitting, super simple model, we are doing quite well to reproduce the observation. So my question is then, can we not, and I'm sure we can, improve also these global models just when we have more observation and consider these observations? I think this is the story here. It has, again, it's not physically based. It's just, hey, well, we calibrate just 2 parameters and get on the global scale such a better fit. I'm sure there are very good and intelligent people, they can do it better and implement this into the models.
But I may follow up. I think that actually makes sense. At the very left end is very humid climate.
Yeah.
Actually, there is not much groundwater recharge. Why? Because the land is very saturated. So water doesn't get on the water table. It runs off. The surface transport is the main mechanism. Floodplains, rock rivers. The very humid end, actually groundwater is pretty stagnant. Because it doesn't move, it's always saturated, it doesn't have a gradient. So that's why it's not a linear curve. If you look at data, there is actually a peak about 1, aridity index is 1.
Yeah.
And so it makes perfect sense. The data shows that. So I think that's the support. Because all our study shows this hump shape. Low, very low, different regime, and then it's some intermediate aridity, and then certain processes kicking in, become more important. So although it's just pure data fitting,
The interpretation, yeah. The interpretation can be put into the context of physical understanding. And that's also, you mentioned this, the change here with the very humid areas. That's why we stop also our calculation here, because here it's changed. We have kind of a tipping point because it's so humid. We have a lot of water. Right. Yeah? Sorry.
One other thought on that reminds me of the Lvovich partitioning, which is some thinking, rather than thinking about recharge directly, thinking about partitioning of stream flow into quick flow that leaves the watershed quickly, and wetting that stays on the landscape and does something, either becomes ET or becomes groundwater recharge. And I think if you think about that component in those really humid places as the quick flow, then the remainder is wetting, and you would see less recharge.
Yeah.
That's an old paper, 1979.
Yeah, right.
Sorry to...
No, it's good, it's good.
Hey, Christian, thanks a lot for this really interesting presentation. I have a follow-up question here, and sort of the idea that you have on climate change and why is it not doing what you think that it's doing. If we assume this model is like this, and we take these calibrated parameters and put them into the climate change model, we're sort of assuming some stationarity into that system. I don't know if you have any thoughts of how to better fit this model for climate change conditions.
Well, actually, I wouldn't use this kind of equation or model for climate change prediction. It's really like just pointing on the fact that these models are not calibrated against recharge, and there's a lot of potential to improve that. I wouldn't do that. I mean, we have done some simple sensitivity calculation, but it's too simple for this important output you might produce, and no, I wouldn't do that.
Thanks for this great presentation. I also have a question about this research. If you can go back to the figure you show, the different models are off from the observed data. Yes, I'm very curious how you got this graph, because it's observed recharge versus model recharge. But the units you use here is millimeters per year. But if I'm not mistaken, that the observed data is the point data, and I saw it's collected from 1980s to 2000. So I'm so curious how you got this.
I mean, of course, we have a scale issue, first of all. I mean, the global models, they have a cell size where they simulate groundwater recharge, and we have point estimates. What we have done is, first of all, we average within every cell to have, yeah, because we know in one cell, depending how big the cell, the grid size is, you might have 2 points, and they might be already a little bit different. So we average for every grid cell. And then in addition, of course, we have a lot of noise. It's still not a good fit. And we were just running a kind of moving average to reduce a little bit the noise and just to, yes, to see more clearly the trend. This is how we have done that. Yeah. I don't know if this answers your question.
Oh, yes, sorry.
Yeah.
Yeah, intensity of rainfall is, supposed to increase, but the recharge is sort of a low-pass filter, and
Yeah.
so it clips off the high intensities.
Absolutely.
So can you talk to us a little bit about how, if we have an increase in intensity, how that's going to affect your calculation?
It will, because yeah, you're right. I mean, we will have more extreme precipitation events. That's clear. Some studies shows that these more extreme precipitation events might lead more to surface runoff at some locations. And actually, I can't tell you really how these precipitation events might influence our long-term groundwater recharge rates. It's really difficult to estimate. I mean, if you have depressions and the surface water comes there and you have kind of more focused recharge, you might have more groundwater recharge at some locations, but this is not considered in our simple calculations. For this, again, I think we have to move to more physics-based approaches, because otherwise we have a kind of empirical relationship, and this empirical relationship is good for now, but if the data and this relationship change in the future, we can't not predict this with this simple equation. So for this, I still would move more to physically based models.
What about your Gardner model? I mean, it must be limited by K-SAT.
Yeah.
And so isn't there a cutoff there? Can you then
It is, yeah. It is. I haven't tested this, but it's true for the analytical solution. Especially the extremes are difficult to reproduce. I mentioned that we make the comparison to, for instance, hydros. Most of the time it was a good fit, but for the extremes, not. Which is also not a surprise, I guess. And that's why I think these kind of models, for extremely changing conditions, dissimilar conditions, we cannot apply this. Again, it's more just showing, hey, we are far away from a realistic model right now. We have to improve this. Yeah.
It seems like a global model would help predict recharge in areas that have less data potentially, or would you say that that might be, I don't know, maybe not the right application of a global model, because then you're trying to predict recharge in a really localized region. Can you describe maybe the limitations and where you would apply this model other than just like meteorological boundary conditions?
Sorry, I didn't get it.
Would you say that you could use like a larger grid model or a global model to predict recharge in areas where there's less data? Is that?
You can, but the question is if your predictions are right. Then I think this is the problem. I mean, the validation is just missing, and I think we need more. It started in the last 1.5 years, more model comparison, intercomparison between the models, how they react, and when we see differences, why we have these differences, and what might be the more sophisticated or more correct approach. And I think just using a model and predicting for a wide part of the world recharge doesn't help, because then we can push the button, we get a result, but what are we doing then with the data? Are they correct? I think this we really need more benchmarks, we need more large-scale observation, we need more model comparison, and I think this is what helps more than just predicting at some location or filling the gaps, especially. Yeah.
There was a bit of a follow-up on that, so what kind of data do you think, I mean you touched on that and I really appreciate it. How can we validate these things at these huge scales? It's very complicated.
It is.
So my question is, do you have any general comments on the kind of data that you think would be good going forward to have to help validate these things, or are we just too far from it? I know it's kind of a...
It's a big question. No, I mean, first of all, as we have also seen in the previous talk, just having, first of all these data, the data should be available, that would already help to figure out how good we are. Certainly we need on the long-term time series, but the problem is still how you estimate it for groundwater recharge. And I mean, if you have long-term data and, for instance, you have the water table fluctuation method under control, you might create some time series, and this further helps. In terms of remote sensing, I mean, you can estimate how the water table fluctuates, and perhaps from there you can also get at least a feeling how recharge might change. I think these are the ways. But still, it's challenging on that scale to validate these models, and we perhaps have to downscale some of the models just for some region where we have more data and see how they perform there. I don't know. Yeah.
I agree though that if you have a bunch of models and they use very different
setups, yeah.
And you get some results that are not so dependent on the pieces, that's, you know,
yeah.
It's better than nothing, even if you can.
I mean, again, it's not against the global models. They are important. They are a tool for communication, information. But just we have to be very, very careful to clearly state the limitations. And I think this is sometimes not so clear. People just take the map and say, well, look at this point, we have a problem. Perhaps we have, but with a huge uncertainty. Yeah. You wanted to add? Sorry.
This is sort of a little bit less in depth, but you've said that groundwater recharge tends to be underestimated.
Yeah.
And I assume that there are lots of models that sort of rely on a global water balance system. So do you know what gets overestimated, where all this missing water goes in global models, or is this not really it?
Yeah, I mean, partly you have seen that the discharge values are overestimated. I still have to read really the paper. I can't tell you exactly where the water goes, but the problem is, I think, a bit in the models, they are calibrated against discharge, maybe ET, so all the mismatches and uncertainties goes into the term of groundwater recharge, and without any validation checking, and so you just threw the uncertainty into the recharge term, and then, yeah, you don't know what comes out. And yeah, I think if you would improve also discharge simulations and ET simulation, of course, this line would move more to the one-to-one line, but I can't tell you exactly where the problem is. Maybe this paper I mentioned here, this presentation might help, I don't know.
Students first. Okay, so recharge is such a fuzzy concept.
It is, yeah.
I never attack it because it's too difficult for me to comprehend. It's so spatial and temporal scale dependent. And for example, the models are, your data is a point. You're on well-drained places. You know there's no natural flow into it. You're just leaving. You can really use lysimeters with deep Vadel zone. You can measure recharge. But if you go to larger and larger scales, you're not only including source but also sink.
Right.
So I just wonder, it's so skill dependent. What is recharge? The net addition to the water table what's the addition to the water table? What's the net result of adding and the discharging? So I cannot wrap my head around it. It's the same with temporal variability. And so if you look at 1 hour's recharge, and then if you look at 5 days recharge had gone to the river, so the water table didn't change very much. So it's so messy, and your distinction and your damping depth is a very clever, very elegant way of dealing with the temporal variability. What are we talking about? At what time scale? But spatially, I just wonder, because if these are model estimates besides yours, the model estimates are from model grid size.
Yeah, you have both.
The larger the grid size, the less the recharge, because you're including more rivers and sinks that pull it out. And the longer the period, the less the recharge. So if you're comparing, maybe the models have a trend. The most underestimating recharge models are the largest grids. I would suspect so. And also, they are, this is annual recharge, right? It depends on the model simulation time step as well. So the temporal steps and the spatial grid really are very significant when it comes to recharge. That's why I don't like recharge. I don't tackle it. It's just too complicated. It's too spatial.
But it's actually quite funny, because the models with the finer scale, they are far away, and the models which are more from the grid scale, and the model which are very coarse, it's closer. So they do somehow a better job. But you're right. We have the scale. We have the grid cell. We have probably the two process, recharge, discharge, in one cell, and that makes a one-to-one comparison difficult. Absolutely, you're right. And
do these models have transpiration directly from groundwater?
No.
Okay, that's another reason.
Yeah.
So
as far as I know, I mean,
if there's no transpiration from groundwater, and based on water balance approach at all, then you have low ET, and so you have higher river flow. So so groundwater as a source for plants is also an issue depending on the models. It's a very tricky problem. I just really admire you for the courage to tackle the spatial temporal variability.
Do you have any other comments? Can I share one further thought kind of related to that?
Sure.
So in Maryland, in the United States, we have a small watershed where we do research. And a few years ago, we drilled a deep well up on a ridge that's something like 20 meters above the valley bottom below. And we have a well there, we have some wells in the valley bottom. And when we first got data back from the well at the top, this isn't like a dramatically, high relief landscape. When we first got data back from the well, we thought, oh, something must be wrong. The water table fluctuation is like completely out of phase with precipitation. So it's like 6 months out of phase, almost. And then you go down to the valley bottom, and it's completely in phase, and it's responding in the storm time scale. So even at this small scale, so like when we're, I guess for me it makes me wonder whether recharge is a useful concept in a setting like that, like a single valued recharge, or whether what is more important is the integrated behavior of the whole kind of system.
That's a good question.
The deeper the Vegas zone, the longer the delay. In the Amazon, where you have valley wells respond to precipitation. Wet season is in sync, but the hills are 6 months later because of the long travel distance from the rain to reach the water table. So yeah, this is another complexity, the offset, on the phase response. You've got tough problems.
No, I mean, probably in terms of water management, we shouldn't use these global things. It's more a kind of a catchment modeling, I think, because, I mean, you're right. You can have one catchment in a valley. You have a higher recharge, faster response, and for some other areas in the catchment, it might be a little bit different, and you might also have different perhaps geology, and this further makes it difficult. Cast, I don't know. So in terms of water management, we shouldn't really use that scale. We have to go down to catchment scale, I think. Yeah.
And I believe none of the models actually are deep enough to include the water table interaction with recharge.
No.
That's another.
No.
It's a free drawing system.
It's often a bucket. Just one fraction of the stream flow goes into this bucket, and that's actually.
I'll send you our recharge estimate as full interaction with groundwater and that.
Okay.
All right, with that, let's thank Christian.